Okay, we take this standard, because it's a bounded function, I can find an m and m that this happens, and an to be the set of all x at that m plus l by lk minus 1. Notation is terrible. Fix an n and look at this. 2 to the n I less than fx m plus lk by 2 to the n. So remember what we did? We looked at m to m. We divided it in 2 parts, then we divided in 2 parts, then divided 2 parts. For the lower function, we took the left extreme value. For the higher function, we took the right extreme value. And similarly, we looked at this synthesis. Then we looked at phi n x to be summation k equal to 1 to 2 to the n m plus l k minus 1 by 2 to the n chi of where eknx was ekn is f inverse of ek. Okay, all those points where this takes place. And for psi n, the super function, we looked at the right hand point. Okay. Now the question comes, well, this seems to be a nice way of doing things. It seems to be a reasonable way of doing things, because Riemann simply bifurcated their partitioned the domain space. More natural thing is to go and look at the range space and partition it. But then what happens is, these are nice fellows who are obviously satisfying this. So all these fellows are valid candidates there, provided I can define the integrals. How can I define the integrals? Provided these sets are have a measure, they are measurable sets, and therefore I must start with a function for which such sets are measurable sets. So that means that is the exact definition of a measurable function. If such sets are measurable sets, that function must be such that if either any one of the types of intervals, like this semi-closed intervals, measurable, then the inverse image of such sets which are measurable, always being a sigma algebra, all intervals get measurable. You can say that the inverse image of a Borel set is measurable, or inverse image of the semi-infinite set is measurable. Any one of that we can take as a definition and then forces that property on you. This Lebesgue way of partitioning the range space, as common sense would say, when you count the currency notes, you collect them up in the order of the denomination, not take the bundle and take first 10, next 10, next 10 and try to count. Okay, so that says the way when you do it, those bundles that you took must be measured. That's what it is. That is one that forces the notion of measurability. And therefore, if EKN are all measurable sets, then phi m, psi m qualify, can be integrated. Because whenever you have such thing, you simply define it to be the value times the measure of that set EKN. This forces the definition of measurability of the function
definition of measurability, inverse image of Borel sets is taken to be Lebesgue measurable.
Yes.
Would it not be more natural if inverse image of Lebesgue sets is Lebesgue sets?
Natural, because this is what got forced.
Okay.
See, at prior I didn't even know what measurability was. I was just going blindly, and Lebesgue said, let us partition the domain, range space. When I partitioned the range space, I ended up with such sets. And if I wanted to integrate such function, I must make sense for the measure of these sets. If I want to make sense for the measure of sets, simply I want those sets to be measurable. That only forces measurability of Borel sets on me, nothing else. So I work with that only. So I take only those that are forced on me. There is no way I have been demand. Why do I ask more from the function? When less works, for a function which satisfies a lesser property, I can do the integration. Why do you want the more restricted way and then reduce the number of functions that I can integrate? Right? The natural way is to ask less conditions and I ask less. Only Borel sets inverse image to be measurable sets. Okay, very good. Is that clear? So that's what that forces the first you would have said, okay, therefore F inverse of such semi-closed intervals must be measurable is what I would have asked. But then that forces all the things that Borel, the sigma algebra nature of these things forces that finally any one of them can be taken as the definition of measurability. Okay, now therefore this class is much richer. This class of simple measurable functions which are less than or equal to or greater than f when f is measurable. So therefore, once again, that seems to be a meaningful thing to work with. But right now I am not going to start with it. This is just to say that this seems to be a very natural thing to work with. Now what I will do is the following. I will simply see that this is indeed the most natural thing to do. So what we want to show is, I will keep this definition which I would like. What I would like is, suppose I don't care whether this class was richer or not. I take this definition because I know this is a non-trivial class, at least all that Riemann had. So I ask the question, one, if suppose the Lebesgue upper, I started only with this now. I have a measurable set, of course I take measure of it is finite, right now what you find in measure, and I define the Lebesgue upper and lower to be this, and suppose by freak I ended up with the upper lower integral is equal to lower integral, then implies what property of f? What?
Excuse me, sir. Sir, AK is an element of A, right?
AK is an element of
A, because it's set of all
yes,
Fs.
yes, certainly.
So you can only talk of F of AKs.
Yeah, when I say F inverse of
AK, what do you mean? Because X is AK is EK. You said EK.
F inverse of
EK
EK of N
is the F inverse of these sets.
of
What should I say? Yeah,
AK.
F inverse of AK.
but AK is an element of A, right?
AK is on the domain set.
AK is on the domain
What should I
set.
write it? This itself? Okay, I'm sorry.
Yeah.
My notations were bad. Okay.
That's it.
You're right. Simply AK, that's all.
Yes, sir. That's
So
it.
here itself I can put AK. F inverse of that interval
Yeah.
m plus k minus 1 by 2 to the n, m plus k l by 2 to the n is what AK n is. Okay, if you want, you call this as
Yeah.
E. That's what that interval should be. You are right, absolutely right.
The top 10 it should be changing.
Which
Here
one?
is the free of AK. That should be. No, that is the top one. AK is equal to.
AKN is equal to the set of all x in A. This is correct, right? All those points. And then this is simply AK. this is not needed, this is also equivalent. This EK definition, to see it as this is one, actually it is the other way around.
Cannot even come.
EK is FK, F inverse of AK. And that, therefore, we say we are talking about the inverse image of a semi-closed interval. That to be a measurable set, and that forces all other things. You are right. Thanks. Okay. So, what was that? This is rotation problem. Right. Therefore, in other words, what is a necessary condition for these two to be equal? That means, what is a necessary condition that F must satisfy to get L upper equal to L lower? This is what this question means. Question 2 is, what condition on F implies this? All these are here. So under what condition will these two be equal? That is, what is the sufficient condition? That guarantees, that assures. I don't use the word guarantee because I am not sure of the spelling. It is AU or UA is always confused. So that assures L integral of B equal to L integral. Okay. So we would like, in fact it would be nice if both the conditions are same, that we have a necessary and sufficient, and that condition is the measurability. For both the answer is F is measurable, F is measurable.
To answer these two questions, do we require this?
No. Right now, that's why for ask the first question, I simply do it. I know that class is not trivial. At least Riemann's things are there. I calculate it, and then ask when will it be equal? And then I'll say that it will be equal forces the F to be measurable. And conversely, I'll show that F is measurable, then it's forces. Okay. When I treat this question, I am getting measurability of F as a final product. Here, I start with F as a measurability as the initial product and get the equality at the end. So therefore, final conclusion would be that the Lebesgue integral is well defined if and only if F is measurable. Okay. We'll see that the answer to both is that FB and the basic sequence. So whenever you have a Lebesgue measurable function, bounded Lebesgue measurable function on a finite measure set, we can define the Lebesgue. So that's what I am going to use. This is the crucial theorem. This is the only theorem in the sense that it tells what exactly are the functions. Okay, I will keep all these definitions, whatever I require that are there on the board. What should I write? What did I write? Fine. Which question shall? Oh, since I have this on the board, I will tackle the second question first. So let's look at question. Suppose F is measurable. Okay. Then I have these for every n as measurable simple functions. So this implies for every n we have the measurable simple functions phi n x and psi n x as that is this two. Okay. Now, what can you say about integral psi n? it is simply this into the measure of that, all that to be added. So it is summation k equal to 1 to 2 to the n, m plus kl by 2 to the n, measure of akn. Now incidentally, what is L? L is the range, m minus n. Then similarly, integral of phi n is equal to summation k equal to 1 to 2 to the n, m plus k l minus k minus 1 into L by 2 to the m. So what is integral psi n minus phi n? Let us first of all maybe let's see what should we do. Okay. What can you say about integral psi n compared to the upper integral?
Difference is
Yes.
L by 2 to the power of n into measure of a.
Okay, first of all, let me write difference. Okay. It is L by 2 to the power of n measure of a. Good. Because the difference is L by 2 to the power of n, sum of the measures of akn. But these akn's form a disjoint union of the whole set A. So the sum of the measures will be equal to the measure of A. So what happens to this as n tends to infinity? 0. So this tends to 0 as n tends to infinity. That's all I have to say. Now, make the conclusion, therefore the upper integral is equal to lower integral. Okay. Now I will put a question mark here. Put the right thing. Therefore, integral upper is equal to integral lower of
Measure of
that is important. Because measure of A is finite, this goes to 0. That is the reason where I use the fact that measure of A is finite. Okay? Since you are right, that is the reason why. See, these are all conditions added later. You start doing it, at this stage you want this, so you go back and put, okay, I'll put measure of A finite. See, you just go on adding so that you can bulldoze your way through. Okay? And then, okay, via all these things, I have at least one theorem where I have all these conditions. Then I will see if this is violated, what will happen, that is violated, what will happen, I will push. So the conditions come later. So we state the theorem, eventually you put it upside down and you put all the conditions first and state the theorem. At this stage, if you did not assume that the measure, it's a good observation, that at this stage if you did not assume that the measure of A is finite, you are stuck, nothing happening. The measure of A is finite, it simply says mess, everything is infinite, what is it going on? Okay. Right, therefore, no problem, when the function f is measurable, the upper integral is equal to the lower integral, so it at least says that for all measurable functions on this set, I can define the Lebesgue integral. I can define the Lebesgue integral by this, I can define the Lebesgue integral by this, it doesn't matter, but all of them are going to give the same result. Fine. So therefore, we got the answer to this question, that a sufficient condition for the Lebesgue integral to be well defined is that f be measurable. But we will say that is the only thing you can do. But no other fellow is it. In other words, we will now sweat out and see, by chance the two are equal, upper and lower, should the f be necessarily be simple, measurable? And we will show this. So let us handle now question 1. So the answer to this, so therefore what you are saying is, the answer is f must be measured. We have seen this, so we will show this also. So if f is measurable, what condition f must satisfy in order that if f is measurable, this automatically implies this. Now we will see the other way around. Suppose bounded and Lebesgue upper is equal to Lebesgue. These are all given to us. We will say that nothing will happen, it has to be measurable. It is not going to happen for any other function. I know that if f is measurable, this happens, but I will now show that nothing for nothing else this will happen. Okay. Now here we see that all the properties that we proved about measurable functions we will explicitly use. That's why they are all put in front. And those are all, they come on the way. Then we put it as a separate lemma and do it in the beginning itself. Okay. So the definition of measurability was first done as, so we put it in the beginning and define measurability. Now we'll see there are some of the properties of the measurable function that will come into the picture, and that will all come in the beginning. Okay. So we are given this is true. Now look at the definition of the upper integral. The definition of the upper integral is this sum number there. Okay. What does that say? It is the infimum. If it is the infimum, if I go slightly to the right of it, there will be somebody to the left of it. So what does that mean? Given, so let us just call it an upper integral, and I am going to look at 2 plus epsilon by 2. So given epsilon positive, I say why epsilon by 2, you put epsilon, you find there is a 2 epsilon coming, so in the beginning itself you adjust it to epsilon. Best thing is write epsilon 1, epsilon 2, epsilon 3, and later adjust all these epsilon 1s so that you get the epsilon that you want. Okay. Then, the infimum is epsilon means, if you go to the right, one of these numbers will violate that. So therefore, there exists a simple function, simple measurable function, psi x greater than or equal to fx, such that the integral of psi will come to the left of the upper integral of f plus epsilon by 2. Right? Similarly, the lower integral, somewhere there, it is the greatest lower bound means what?
Move to the left, there is somebody to the right.
Huh?
Move to the left.
Move to the left.
There will be somebody to the right.
Move to the left or the right?
Left.
Huh?
Left.
Move to the left. I move to the left. What happened?
Somebody to the right, to the east.
Somebody should be to the right. Why? Because otherwise this fellow will become the greatest lower. So therefore, what does that mean? There exists a phi belonging to SL and A such that phi x is less than or equal to fx and integral phi is now greater than or equal to right. Okay? I will call it as, because they all depend on epsilon. So I have got this. So what do I get about what can you say about this? This is, the first one is less than this is greater than or equal to this, therefore the minus of this will be less than or equal to this. So again, minus L, but what is given to us? The upper integral is equal to the lower integral. So given this implies Integral A psi epsilon minus phi epsilon. We have seen that the integral is linear for the simple function. So phi minus that. So this is less than epsilon. Because given L upper integral. So we have got this. So what is the conclusion? Given an epsilon positive, there exists a psi and a phi satisfying these things. Phi below f, psi above f, such that the difference, the integral of the difference is smaller than epsilon. Now, I do this for every epsilon equal to 1 over n. So, for epsilon equal to 1, epsilon equal to 2, epsilon equal to 3, etc. So, I get a sequence psi n and phi n. Do it for get the sequence phi nx, the sequence psi nx, all are simple measurable functions. Phi nx less than or equal to fx less than or equal to phi nx for all n, because that's how it has been constructed. Then integral psi n minus phi n is less than. Now what is epsilon? 1 over. Right? So for every error, I sort of make the errors as discrete errors. 1 half, 1/3, 1/4, 1/5. But any epsilon n going to 0 will do. Okay? The normal thing is 1 over n. Take any sequence of epsilon n is equals to 0. So choose standard 1 by n and then construct a sequence which has this property. Now you see, I want to show that f is measurable. My aim is eventually say that see whether that thing is the sufficient condition, necessary condition also. So our aim to see if f is measurable. There is that force. Then I would have a need necessary and sufficient condition. Let's not forget this aim. So now what I do is, I can't take limit of phi n because I don't know now the way I have constructed. I don't know whether it is increasing or decreasing. I don't even know whether the limit of phi nx exists. There is no way I can start. So what I am going to do is, I at least know that the phi nx are approximate at each point. The phi nx are all approximating fx from below. So at each point you get the best approximation. In other words, define phi x to be supremum or infimum? Supremum, because they are underestimates over all the x. Similarly, phi x to be the infimum. For each x do this. Now we add a thing. If these were measurable, it would have been nice. Because I want to bulldoze through measurable functions only. And include a theorem that the class of measurable functions is closed under infimum, supremum, max, min, limit, everything, lim, sup, lim. So, because these phi n's are psi n's are this thing, phi and psi are I can't write measurable simple now. It is not necessary that the infimum of simple functions is a simple function. All I know is that it is measurable, okay? So the simplicity is lost. Because I have to reach a function which is not simple. I want to reach that function f, which is not simple, but I want to show measurable. But I am saying that I can reach this function phi which is not simple but measurable. But I asked you to reach f. But you reached phi. Then what I will show is I essentially reached f. What do I mean? Phi and f are equal almost everywhere. We will show that phi and f are equal almost everywhere. Then we prove the theorem that if somebody is measurable and another fellow is equal to him almost everywhere, that fellow is also measurable. You see, all those theorems come later, but they are put in front. That is the bad thing with the way the mathematicians are. Those theorems look like magic, but suddenly he produced a theorem just because it is absolutely necessary here. I could not approach F, but when I tried to do this phi, I approached something else. Then I started, how bad is this fellow to F? Because he couldn't be far away because phi n's were approximating F. And the phi n's are approximating phi also at each point. So if there is something so very difference between F and phi, I find the difference could be only almost everywhere. They could differ only on a set of measure 0. Whenever a set of measure 0, it must be insignificant. And I prove that insignificant theorem that if two functions are equal almost everywhere, and if one of them is measurable, the other fellow must be measurable. That's what the theorem is proved last time. Okay. So we have this phi and psi. Now clearly, for any x, phi x is less than or equal to phi n x. Why? Because which is that? What is that? Let me not hang around. Phi n x is less than or equal to phi x. Is that correct?
No.
Phi n x. Similarly, psi n x is psi x is less than or equal to phi n x. Okay. Phi n x less than. Right, I'll come back to that. What can you say about the between phi and psi?
Already shown that they go lower end.
Huh?
So any for all n,
Less
xi is less than that.
Phi x will be less than or equal to
Psi
psi x. That will also be there. Okay. It's necessary. We'll use. I don't know what are the things I need. So as we go along, we'll see which are the things that we need to this. Alright. That's what I need. So okay. Phi x is less than or equal to psi x. Eventually, what you see is these polars are from this side, these polars are this side. The phi n's and psi n's are neatly separated. Phi x is less than or equal to psi x. Is it less than or equal to? Because each phi n x is less than or equal to f x. They are both supreme also. So we have got this situation. Now, see, which are the two fellows with I am comfortable? I am comfortable with phi and psi because this fellow I am groping. I don't know what sort of fellow is he. So okay. So I am comfortable with these two fellows. I know that I have reached them through simple functions. I know that I have reached this fellow through simple functions. So I have a handle of this, I have a handle of this. I know this fellow is measurable, I know this fellow is measurable. I want to show that one of them is equal to this fellow almost everywhere. That will be done if these two fellows are equal almost everywhere. Because this fellow gets sandwiched in between. So it is enough to show that phi x equals psi. That's the cleverness. Okay. So all that earlier theory, see, when you work on your thesis or a problem, you find that the worksheets are totally messy. But when you write the thesis, finally you write it all in beautiful format, and though it came just like that as a magic. But after a few days, you yourself read your thesis, you don't know, where did I put this? Where did I get this from? Then these scrap sheets are very, very important. I remember a very interesting story which involved me several years ago, which is really once upon a time, I should say. Several years ago, I joined after a master's degree in mathematics as a research assistant in the Department of Civil Engineering, about 45 years ago, more than that. November 1961, okay, 45 years back. And I was assigned to a project, huge project, which involved some aeronautics fellows will be here, turbulence motions, okay, turbulence in general. and I struggled through reading two standard textbooks in turbulence. One was J.O. Hinz. Is there any aerospace person here? Nobody is here. Yeah. Have you seen J.O. Hinz or G.O. Hinz?
But I am guidance.
Okay, guidance. See, that's what specialization these days means. An aerospace engineer says, I don't know turbulence. Okay, turbulence is bread and butter. Okay, the other one is G.K. Batchelor, the famous applied mathematician. Okay, mechanical engineers would have read it. So when we read, I used to read, and there were two other people. Professor Govind Rao, who was the only professor and head of the department of mathematics. He would say there was another senior person. I had to lecture to them because they were also trying to learn turbulence, but they knew it as a hydraulic engineer. They knew the mechanics of it, but the mathematics of it, they had a problem. So there was a paper of Batchelor that was being referred to in one of his articles. So we took that paper and started reading. There was some calculation in it which involves horrendous things about tensors. So Batchelor wrote after some simple algebraic manipulations, typical Batchelor way of writing. It really hurt you when he says after simple algebraic manipulations, you get this. And then Professor goes out told me, you do simple algebra, show me how you get this. So I struggled for 15 days, maybe about 18 pages of calculations, horrendous manipulations with all those tensor indices, and I got the answer. Luckily I got the answer. Then I went and said, sir, I got the answer, I presented it. And then I finished it, Govinda said, do you call this simple algebraic manipulation? This is horrible. So sir, this is the only way I could get it. They said, write to Batchelor and find out. I told him, no, this is the only way to get it. No, don't argue like this. You write to Batchelor and find out what happens. So I wrote to Batchelor, and I was very simple fellow at that time. I enclosed all my calculations in my letter and said, this is the simple algebraic manipulation I could get. I would like to know what is the way you got it. It took, of course, in those days there was no email, nothing like that. Only Indian Postal Service and the British Postal, Her Majesty's Postal Service were involved. And after about 2 months, I got the reply. Batchelor wrote 2 lines. I don't remember how I got it, but I can assure you it was longer than yours. This was his reply. So I went triumphantly to Mr. Govindra and showed it. And in fact, he wrote, thank you for sending me your manuscript. I will keep it now safely in case somebody else asks. Okay, so I showed it to Professor Govindra and said, look here, I got it. I am better. So better to keep those scrap sheets rather than a copy of your thesis. A copy of this will always be available in the library. It's the scrap sheets which you will find it more useful. And this is what all Lebesgue went through. Well, it is not necessarily the complete fine tuning of all that Lebesgue did. But eventually many other fellows joined in, put these things in proper languages and things like that. But the essential ideas are Lebesgue's. Okay. So therefore, what Lebesgue did was, I could get to this function through simple measurable. I could get to this function through simple measurable. If I show these two are equal almost everywhere, then that will also be equal to f almost everywhere. And f will be equal to a measurable function almost everywhere. And therefore it is done. So therefore, only thing, so it remains to show. So that phi x equal to phi x. Okay. Is the logical sequencing fixed correctly? So what I did was, suppose the right hand, left hand, upper and lower are equal, I could construct for every epsilon 2 simple functions, and I did it for every epsilon. So I get a sequence of simple functions, and I look at the superteams. They get the f's get sandwiched between these two, and these two turn out to be measurable functions. And if I show they are equal almost everywhere, then f will be equal to a measurable function almost everywhere, and f will therefore be measurable. That is the series of arguments I go through. So that is why Even with my own mathematics spent for 40 years, I argued with them. When you prove a theorem, don't worry about, suppose I can interchange these two. Oh, can you integrate? What is the condition required? Don't worry. Interchange, do it and see what happens. If something interesting comes, you can go back and worry whether this thing. Nothing interesting comes. Why do you waste your time breaking your brain now? What conditions are necessary? This, that, and that. Keep going. At the end of it, anything fruitful comes. It's worth going back and investigating all that. No, right at the beginning, under what condition should it be in LP or HP, 1.5, all kinds of solar spaces I put in the beginning itself. It's all sheer nonsense in my opinion. You go through what your conditions will come naturally. At this stage I am stuck. I want to proceed. I want to proceed because at the end I am going to get something. Not because I proceed and see what happens. If I had been allowed to proceed, then I will see that at the end I am going to get something interesting. So it is better to make myself proceedable. So what conditions are needed? That's why. Otherwise, it doesn't matter whether you allow me to proceed or not, because anyway nothing I am going to get at the end. Okay. So that is a problem with, in fact, I really get annoyed with some of these partial differential equations for those who write the paper. They will start with some horrendous Fourier spaces and conditions and indices conditions and growth conditions and state the theorem. At the beginning, I don't understand why are you starting with all this? First tell me what you want to do, then I will decide whether I should grant you this or not. Not like that. That is, I think, a fundamental problem in the technique. This is because of highly professionalistic competition. If I write it in such a way that you don't understand, I think Fermat used to do that many times. I think Fermat is simply write some statement and say, I got a proof of it and tease his British friends or whatever it is. Okay, that they would struggle all day trying to find out what is the proof and things like that. Apparently, there is a story about this. Early days of the Institute for Advanced Studies in Princeton, very famous place in mathematics. This is a joke. I don't know how much of it is true. Everybody, when I asked this question, the IISc Institute, they call IIS fellows. The Indians call them the IIS fellows, the Institute for Advanced Studies. Anyway, they always laugh and say it's a joke, it's partially true, it's in spirit true, all kinds of things. They never say whether it was true or not. Apparently, there is a corridor that separates the physicists and the mathematicians in the Institute for Advanced, at least it used to. So the physicists were very sort of wary of the mathematicians. Then I didn't want to talk to them because the mathematicians were always trying to put things in a language they did not understand. So, or make fun of the. So what they would do, the physicists, if they had a difficulty, they would go and put that question in the bulletin board. And some mathematician after a cup of coffee going there, see this question, right there, of course it's obvious. And then walk away. And there the problem starts. This guy is not afraid to ask anybody else. It's so obvious, I better figure it out myself. And many things have been figured out by the mathematicians, by the physicists, by this trick alone. So they went back and worked pretty hard and they figured it out themselves. It wasn't obvious though, but at least they figured it out. So there's some sadistic pleasure in this, rather than the pleasure of solving the problem. This gives them more pleasure. Anyway, so this is what we want to solve. We want to eventually show that this phi and the psi we got through the sequences phi n and psi n are equal almost. So let us look at this set of all x in A for which phi x is not equal to psi x. So we want to show that the measure of E is measurable and the measure of E is measurable. Okay. We want to show that this set is measurable. This is obviously measurable because these two are measurable functions. Okay. And phi is always less than this. So the set of all x where phi x minus psi x is less than or equal to, or psi x minus phi x is greater than or equal to 0 is measurable, and therefore equal to 0, less than or equal to is measurable, equal to 0 is measurable. That's its measurability is trivial, and we want to show that this is equal to 0. This is our goal. Now, problem now is boiled down to this. Eventually, therefore, the sufficient condition investigation to show that the sufficient condition for Lebesgue integrability is actually measurability boils down to finally showing that this set has measure 0. Now, I am going to write E. At least first I will write that. Is that true? Because phi x is always less than or equal to psi x. So you want to remove all those places where not equal to psi x, so it is going to strictly less than psi x. So we are looking at this set. We want to show that this set is measure 0. Now, take any x. Phi x is here, and if it is strictly psi x is, if it is strictly less than psi x is there. So there must be something in between. So we will find a sufficiently large integer such that psi x minus 1 over n will be less than. So this says, so x belongs to E if and only then x is a positive, it implies first, then x is a positive integer n such that phi x is less than psi x minus 1. Do you agree with this? Conversely, if there exists a positive integer, obviously x belongs to E, because if it is less than psi x minus 1 over n, it is less than psi x and therefore it is E. So x belongs to E if and only if there exists a positive integer n such that phi x is less than psi x minus 1. Now, how do I write this set mathematically? For each n, consider this and put them all together. That will give precisely this. So, E must be equal. Because if there exists a positive integer, there is a set here, and conversely this. Okay. So, therefore, E can be written like this, where n runs through. I will use different n because I use the n for the sequence there. So I will write a k. Okay? Let me call these sets as E and K. No, E, K, that's all. No E. I call them as set of all x in E. So that phi x is less than phi x. Now I want to show that the measure of E is 0. Suppose I show the measure of EK is 0. Done. Right? So even if I show that the measure of EK is 0, so if we show that measure of EK equal to 0 for every k, because the measure of E will be less than or equal to the sum of the measure of, so E is equal to union k plus n Ek. Well, by monotonicity, the measure of E is less than or equal to the measure of Ek for every k. So measure of E should be less than or equal to 0, but it can never be 0. So measure of E is 0. So it's enough if we show that the Eks are measured. See, finally, I'm boiling down to something which I can handle. Now, what are these Eks? Suppose I take a point x in Ek. phi x less than phi x. Now, I go back to things which I know. What are the things which I know? The phi n's and the psi n. Those are the simplest below. I want to finally boil down the problem to the phi n's and the psi n. Phi is the supremum of all these phi n's. So, phi n x will be less than or equal to phi n. For what n? For any n. So, for all n, I have this. And of course, this is less than psi x minus 1 over t. But psi x is the infimum of the psi n. So, it will be less than psi n minus 1. So, therefore, it implies phi n x is less than psi n x minus 1 over k for every n. Okay, is that clear? So therefore, I will write, this implies x belongs to the set of all x in A such that phi n x minus psi n x are less than 0 for every n. If I call this set, there are two indices now, E and K, then this says x belongs to E and K. So x belongs to Ek implies x belongs to E and K for every n. Now what does that say? If it has to belong to that, it says x belongs to the intersection of the now I don't have to write every n because it belongs to for every n. X belongs to the intersection. So therefore, E is contained in the intersection of E and K. Every point of E is in this intersection. So its measure is going to be Ek. X belongs to Ek. So the measure of Ek is going to be smaller than each one of these. Now suppose I say that as n drops off, this drops off to 0. I am finished. Suppose I show that the measure of Ekn goes to 0, and then goes to infinity. Okay? So therefore, what do I get? Measure of Ek is less or equal to measure of Ekn for every n. If we show measure of Ekn tends to 0 and tends to infinity, we are done. Okay? See, finally now I come to measure of Ek. So therefore, we had a patient who was a cancer patient. We have now converted him into a pneumonia patient. These phi n's and the psi n's are the ones that I know. I know only how to handle psi n's and the phi n's. I finally reduced the problem by going on looking at when will this happen, when will this happen, when will this happen. And I got the problem to the phi n's and the psi n's which I can handle. So therefore, my problem is to show that the measure of the Ekn's go to 0. This is one proof I like because it's simple, it involves simple functions and it tells how a proof should be worked out. Really, it's very, you start with difficult fellows and reach the simple fellows and reach the top fellow, and then the top fellow's requirements you bring it down to the simple fellow, and then you see naturally, finally, the whole thing boils down to asking a trivial question about a trivial simple fellow, and there the story ends. So there is a proverb in Tamil. I am a Maharashtrian by ancestry. My mother was Maharashtrian, my father was Kannada. I was brought up in Tamil Nadu, so I went to school in Tamil Nadu. So whatever language you learn in school is the one that sticks with you. You may go to England, you may go to America, and finally, in a real crisis, the original language will come out. Okay, that's that I observed. I observed even people who have lived for 40 years, 50 years in the US. But still, when it comes to some crisis, the original language only they express. Anyway, there is something called the onion. There are several layers. But you remove all the layers, there is nothing in it. There is Urithu Parthal Vengayathil Ondrum Irukadu. You have heard of it? Is there anybody who speaks Tamil here? One, anybody else? So Urithu Parthal Vengayathil Ondrum Irukadu. If you go on removing the layers, finally there is nothing. It's a trivial affair. Okay? Onion does not seem to have anything interesting. That's what it is. You go on filling out that difficult players one by one. Finally, you find it's a trivial affair. Okay. So that's what we have trivialized this problem. And my friend Balaram used to say the strength of a theorem, the depth of a theorem is determined by, according to him, the quantification is how long does it take to trivialize the theorem. Okay. Right. Okay. So now where were we? So we want to look at this MEKN. Where was MEKN? Okay, let me just write it as EKN. I'll write it like this. What was our set? I'll write it in this form. Psi nx minus phi nx 1 over k is less than that. I will put 1 over k is less than psi nx minus nx. Okay. Now I am going to look at a number of functions. Look at this function. So in other words, I am taking this as the value. Look at this function. What is the comparison between these two? This fellow is always smaller than this fellow. Because 1 over k, because both of them are non-vanishing only on this set. But on this set, this fellow is smaller than this fellow. And then look at this function. What's the comparison with this fellow and this fellow? This fellow is the same as this fellow on this set. Outside this fellow may still exist, but that fellow gets killed and he is positive. Therefore, we have this. Okay? The reason why I am doing it is I know only one thing, namely that the way I have constructed it, this was 1 by n. That's how I constructed it. So I am taking everything back to that. Now, what can I say about f1? Simple function. f2? Simple function, because last time I showed that if you have a simple function and multiplied by a characteristic function, it is a simple function. What about this?
It is also
It's a simple. So all these are simple functions. Therefore, on simple functions, the integral is monotone. If f is less than or equal to g, integral f is less than or equal to integral g. So everything has been brought down to simple function. But what is the integral of f1? It is just 1 over k measure of EKN. I will straight away the last part. The integral of this will be less than or equal to 1 by n times measure of, because you could have taken one more function, 1 by n times characteristic function. So therefore, what do you get? Measure of EKN is less than or equal to k by n. MA is finite and this is true for every m and tends to 0 and n tends to 0. So that's all. So that was all that was there. I already manipulated psi n minus phi n to be less than 1 over and that integral goes to 0 and that's all I want. For every fixed k, the measure of Ek is 0. If the measure of Ek is 0, measure of E better be 0. It is smaller than every one of the Eks. And therefore, phi x equal to psi x almost everywhere. And therefore, phi x equal to fx almost everywhere. Since phi x is measurable, fx is also measurable. So it's a very fine piece of analysis. This is what proof is. So theorem, A measurable set, measure of A finite, F mapping A to R bounded, then the Lebesgue upper integral of F is equal to Lebesgue lower integral of equal to only F being a measurable function. So the measurability of a function is the one that makes things work.
So, do you need MBA there or is it?
I need MBA. Because this is the function which is constant 1 over n on the set A. See, phi psi n minus, okay, if you want to write one more function there. F4 to be simply 1 over n chi ax. Then this is less than equal to F4x. And therefore straight away I can so this less than equal to F4x, which is 1 by n measure. Okay, so that's what it is. But essentially, therefore, eventually I have brought out the integration of a constant function 1 over n and then comparing it with what we have. So, measurability is the key thing for Lebesgue integrals. Measurability of a function. And we have not yet seen about Lebesgue integral, what is the key thing, what sort of function we said that if it is finite number of discontinuity I can handle, etc. But what is the necessary and sufficient condition for a function to be Riemann? That we have not yet seen. But at least for Lebesgue integrability, for the Lebesgue integral to be well defined, the function f must be measurable. All this so far only for bounded functions on a set of finite measures. Okay. But once we cross this hurdle, I have no problem removing that boundedness hypothesis and removing the finite measure hypothesis. It will define the integrals for other places. So let me just point out this. So are there any questions? Somebody has some good music. What's the raga?
Mukhari.
Huh?
Mukhari.
Must be a tape which the other day when we were sitting here and when I was going home at 8 o'clock in the night and we had I was working and just then Jamadevini was also leaving and so he said I'll drop you. I was about to telephone to my house for the car, then he said no, I will not be on the day. When we were going on this car, we had this FM radio was playing a nice Bhairavi. Then at that time I made a remark that everybody sings Bhairavi but very few people sing Mukhari. And he said, no, that you told that, it occurs to me. And I think on Saturday, that was on Friday night, on Saturday I went hunting for some CDs of Mukhari. I think he has got one. So he is playing it. Otherwise I think very few people would play Mukhari. Okay, anyway. So let me just look at the situation now. A general measurable set and a general function. Could even be unbounded, could even take possibly infinite values, but for the time being we will hold it because that part is basically only trivial thing that they handle. Okay, that could be handled. Therefore, as I pointed out, if we take two functions f plus and f minus, f plus x will be fx max 0, f minus x is minus f or fx means minus fx max. What does that mean? F plus x is equal to fx if fx greater than or equal to 0. 0 is 0. F minus x is minus fx if fx less than or equal to 0. If 0 is fx greater than 0. Now the reason why I pointed out to max and min is suppose of course f is measurable. We know now that the measurability has to play some key role in all these things. So let's take a measurable truth. Now we already seen constant functions are measurable, max of two functions is measurable, min of two functions is measurable, or minus of a measurable function is measurable. So these f plus and f minus are measurable. And what about that function f? Function f can be written as f plus minus f minus. And anyway I want the integral to be linear. Okay? So if I can define f plus and if I can define f minus, I would naturally define f plus integral f. Provided one of them is finite. If both of them are infinite, I have infinity minus infinity, that's a problem. So let's assume that for the moment we are handling sense. So, but anyway, what else can we say? F plus is always non-negative. F minus is non-negative. Therefore, the key problem is defining the integral of a non-negative function. So, while I have compromised, when I said that I am not going to take any set A, could be infinite measure, I am going to take any measurable function. I say it's enough if I deal with non-negative measurable function. So, therefore, basic problem A belongs to Vittal, F mapping A to R, fx greater than or equal to non-negative. How do I define the integral? So how do we define that? The thing is, simply estimate to what already you know. See, this is the same trick that goes on. Whatever you know, through that you try to find that you don't know. So therefore, it all depends on how much you knew to start with. Because you'll be playing around with that only. the process. So you can look at it this way. The process by which you build, how fast you are building, where you are going to reach, will be different for different people depending on where they started. Because that's where they are going to build. If you already had enough to start with, then you are going to jump from there. Some other fellow may take a time to reach that place. So it depends on where you started. So therefore, probably there is the genetic code that is given to you is your initial condition. From then on, how you use that initial knowledge is your evolution. Okay, so therefore, this is the problem. So what are the things that we know? We can handle this. We can handle this. Neither of it has been given to us. I should somehow come to this. Okay, so what I do is, first of all, you want me to integrate this, but I will integrate this. What is it? What is H? H bounded. I know only to do that. Okay. But even that I can't do that on A, because I do it only on sets of finite measures. So what I will do is H bounded. The set of all x where hx is not equal to 0, that measure is finite. The other part is irrelevant. The function hx is 0. I take the integral, the flat curve. So the area has to be taken as 0. So that I will take it as 0. So I will look at only functions which are bounded. What I say is the support is of finite measure. It's not equal to 0, only on the set of minor. If I take that fellow, I can integrate this on A. Why? because suppose I call, what should I call it? I call it as SH. Then I can define it as A H chi S is simply the integral over SH of H. So therefore I can do the integral of that. But then I have to estimate this f through such functions. But if I want to estimate, I don't try to go and sit on top of an unbounded function. You will always try to catch up with an unbounded function. So you would like to take Hx less than or equal to. So what I do is, now let me call that as Hf. So let Hf will set up all functions Hx such that 1. Hx is measurable.
So you are assuming SH has finite measure. You are assuming SH has finite.
Yeah, that's what I mean. The measure of only such functions I will take. The measure of the place where it's not equal to 0 is finite. Okay. That's why I am going to take all those functions Hx measurable such that the measure of Hs is finite. 3 Hx is less than or equal to. I am going to take only such functions. Then look at a integral of h over a. Well, it's the same thing as integrating sh over h over sh. By definition, it is simply integral over sh. Because the other places it is 0. That part is right. Now, this is obviously a underestimate of what we are looking for, because h is smaller, the set is smaller, everything is smaller. So we have to take the best of the underestimate. So take the supremum and define integral as done. And now then say it has all the nice properties. It is linear, the f is less than or equal to g, integral f, all the nice properties that you want, you show that is simply technical verifications. Just here also, even in the previous case, having defined the integral over finite measure set, we have to verify that all the nice properties of integrals are there. It is linear, integral of f plus g, integral f plus integral g, integral f is equal to a times integral f. F is less than or equal to g, integral f is less than or equal to integral g. All those nice properties can be proved from the definition. Then you go through this, define the integral of f by this, and show now this integral which has been defined for non-negative functions over probably an infinite measure space and probably unbounded functions. Show that this integral that you define satisfies all these properties. Okay. Therefore, you will have this integral of non-negative functions. Then you define the integral of general. This is the general level as integral f plus minus integral f minus, provided both are finite. If one of them infinite also, it's okay. If this is plus infinity and that's finite, we define the integral to be plus infinity. If this is infinity and this is finite, we define the integral to be minus infinity. If both are finite, we say the function is integrable. Okay. So we have a nice category of slow pulling. So therefore, what do we have? We started with simple functions. We defined the integral. Okay. Then first we have all this. Then we went to measurable bounded functions. We defined the integral, starting from this. But then every fellow here can be thought of a fellow here also. So his integral can be defined through this definition or through that definition. But then both of them are same, we should say that. Therefore, this is exactly extending the knowledge is what is to be established. Then we went to non-negative, measurable, any measurable. Then we define the integral. Then we define general. Any. Now, every one of these fellows can be thought of from this case. So, whatever integral you got this way and whatever integral you get this way, these two must coincide. And those are all very, very simple technical verification. So, eventually, you go to the notion of the. So, Lebesgue, by step over to Riemann. First he said interval, fine, I do it on interval. You can integrate, I can integrate. Your value, my value, same. But I can integrate more, so you lost. Or even on interval, Riemann has been overthrown. Now he says he really goes beating. He really goes beating Riemann. He says, okay, I've already beaten you, but I'm going to give the knock, what they call as the sucker punch or the knockout, beating the Tamil. I'm sorry for using Tamil because there's only there is something called dharmadi. It's a slang. What it means is a very nice fight is going on in the street. Okay, a nice strong fellow is beaten up a weak fellow nicely. Then the weak fellow going in the crowd he also goes and beats him because he knows now that guy is knocked down completely. I will also go and beat him. Okay, it is like that. So Riemann has been knocked down and he doesn't leave. Just gives the punches in such a way that he will never get up again. Okay, so what are the punches that he gives? He says, okay, I am now going to go from a finite interval to a finite arbitrary measurable set. You can't do it at all, you are stuck with intervals. Then he says, you see, I am going to remove all your boundedness of the function, I am going to remove all your finiteness of the measure, everything I am going to do a general integration. So it's a huge extension of the ideas that Riemann had, but he bet in a way, it is not. See, the way we put it is only we are sticking to real. But if you look at the physical questions and where Lebesgue writes his thesis and all, they always had n dimension in their mind. It is not just one dimension. There are many other things that have to be kept in mind in this. But we have sieved out the basic part of it and look at these things. What are all the questions that they had in their mind at that time? See, for them, length was one thing which had to be generalized. But from length, we had the notion of an area in 2 dimensions. Okay, so if you want to integrate a function of 2 variables, what did you do? fxy dA. What you did was you divided the base into a number of rectangles, erected parallelepipeds, calculated the area and took the upper, lower and integrals and all. The same idea worked. Again, Lebesgue, I will do that there also. You divide them into number of rectangles. Now I am going to divide them number of arbitrary sets. What sort of sets? How did you define the interval? How did you define the rectangle? An interval here, cross an interval there. Now I will take a measurable set here and cross a measurable set there. And then generate the measure out of this. Same constructions I will go through and I will get the Lebesgue measure on the plane. Now I can do the Lebesgue integration in 2 dimensions once I have the Lebesgue measure. Then volume, 3-dimensional content. They call it content. Okay. So n dimensions in general. Okay. So it's not just the real line, but all the ideas are contained in the real line construction. Because once you have this idea, you can abstract it and go back and look at anything for that matter. But that's not the way Lebesgue did it. Lebesgue did it in a very. In fact, it is okay. I think I'll stop here and then look at the general integrals, etc. Again, properties, and then I'll come to various other questions like approximations, convergence, important theorems on convergence, etc. It will be very interesting sometimes to read the original. I think the original of Lebesgue is there in our library in the form of a book translated into English. Try to read that. Then you will find it is not as the way Buddhism writes. It's not the way as Royden writes, it's not the way as I said. It will be in that language, keeping that volume, area, content, the word subadditivity, countable additivity will all be later. It come as we're discussing and things like that. Very interesting. Similarly, I wanted to, for example, when I teach Fourier series, we simply say f is expanded as fn e to the int or sin nt, and fn is equal to integral 0 to pi, whatever that formula is, and we get. Fourier struggled, really struggled. The way Fourier found the coefficient was terrible. He evaluated both sides at several points and set up a system of equations and tried to solve that equation. So what Fourier did was, he assumed that there is an expansion, and let's say I will write it in the complex form, instead of sin nt cos nt. And what do we say? An is 1 over 2 pi plus of e to the in. I don't do my course this way, I don't know that. That's how we write it. But that's not the way Fourier did. What he did was, he evaluated a number of points. He said, let me truncate this. And then evaluate it at n plus 2, n plus 1 points. And then solve for a. I've got an equation, system of equations, and solve for a. This is the way we did it. This is terrible actually. Later Saul realized it's orthonormal expansion and things like that. But you can't deny the credit to the even thought of. In fact, this is essentially in some way saying that sampling. He had that sampling idea built. You sample that function at 2n plus 1 points, and that's what Shannon sampling theorem is. If you have a function with band limit, finite band limit, then by sampling it within the sampling density, you can recover the function completely. Now, that theorem had to be given reborn again and again and again in several forms, even though that is exactly the way Fourier did. Exactly the way Fourier did, evaluated a number of points, and then from there sort out the ans and then reconstructed the function. Then this was seen as a problem in interpolation by Vittal, then subsequently seen as a problem of sampling by Shannon. So sometimes it is there at your face staring, but you are not seeing is different from looking. Listening is different from hearing. Okay. It's there. Same music might not have gone into somebody else. For some it is beautiful, for some it's a disturbance. So it depends on what you are looking for. You are looking for something. So therefore, what are the frequencies that your ear likes, etc., etc. So sometimes it's nice to read the originals, because there are lots of things hidden in that. Though they were written in a clumsy manner, much worse than what you may find in a textbook, but the original seeds of these ideas are all there. In fact, that is why Abel's very famous quotation is always read the masters. For example, if you want to read the beautiful theory which was developed in the first 20 years of the 20th century, which is the generalization of matrix theory into infinite dimensional so-called compact operators, you can't beat what Friedrich Ries has written in his book, because most of these are his work. You cannot find any other book explaining it in any better clarity than his book. You have a number of books have come on functional analysis, operator theory, blah blah blah, abstraction, generalizations, etc. Ries is Ries. The clarity. For example, he will not put the definition of the word completely continuous operator, a compact operator, until he comes to a stage where that is absolutely necessary. Because that is the way he worked. He knew exactly, but if you take a book on operator theory, you will see the compact operator is said to be a compact operator, blah blah blah. Why should I say it that way? Where was the need? But you will see read Ries exactly at that space. At this stage, we will make this assumption in order to proceed further. That assumption is taken as a definition that the operator satisfies these properties. Then beyond, because he wants a limit. If that limit exists, then everything of his argument goes through. So I will take only those operators, at least for those with this limit exists. What is that requirement? That is the definition of compactness. Well, how beautifully they write. That is why original readings are always essential. Sometimes I had a friend by name, I would say friend, guru, teacher, philosopher, guide, etc. In the TF center here, Professor Bala, he is now probably close to 90. 81, 26 years. So he's about 86, 87. He had all originals. Whenever he went abroad, his job was to go around the old bookshops, collect original lectures of Riemann, original lectures of Hilbert, some books like that. And many a times, I used to borrow some of these books from him. This is a great pleasure in reading this original. So that's why I say that sometimes it's better to learn things by yourself. Most of the time, these books spoil us, teachers spoil us. It is better to go and look at the original work, and you will find that there is much more to it than what the teacher said, much more to it than what the book said, much more to it than what the review said. There is a lot more in your master's work. I think that way, Lebesgue changed the way analysis was done. Completely. The way analysis is done, their analysis is done, what sort of questions, how you do things. I think he put things in the correct perspective properly. And every one of us was immediately afterwards reached over. The moment the standard integral was defined and the generalizations of the finite dimensional spaces were very clearly seen in concrete examples of the so-called LP spaces, then the generalizations were there for the asking, and they were all beautifully done. So I think that first 30 years of analysis in the 20th century was perhaps solid analysis, which perhaps was the next major step after Riemann and others. Until then it was groping. Riemann was perhaps the last. Afterwards, till Lebesgue came. And it so happened, see, Lebesgue was there, Hilbert was there at the same time, Friedrich Ries was there, Hellinger was there. Some of the finest names of analysis were all at the same time in that same European region, which really made analysis flourish like that way. Von Neumann also. So that part of analysis is what really analysis is, classical. Classical analysis as it stands today. And Lebesgue is probably the starting point for all.